So our strategy when we approach a problem like this is to first find the antiderivative, and then we're going to evaluate it over the interval from 2 to 0. So we can apply all of the properties that we learned on Tuesday, all of the different steps. If we want, we could separate it. I'm just going to write some symbols in here. We could separate and take the integral of each piece. Okay, we could take that approach. I think that very quickly you become used to just taking the integral as a whole. You don't need to make the step of breaking everything up. You just realize that we take the antiderivative of 2x cubed, and then 6x, and then 3 over x squared plus 1, and it all just kind of comes together neatly. So the first thing we want to do is find that antiderivative. So we need first the antiderivative of 2x cubed. So who can give me that? That's it, 1/2 x to the 4th. We bump that exponent up 1. We divide by the new exponent, which brings 2 down to 1/2. All right, what about negative 6x? What would that become? Negative 3x squared. Again, bumping that exponent up by 1 and then dividing by the new exponent. So the tricky one is this piece right here. All right, so what we want to do is look at that as 3 times 1 over x squared plus 1 and look back at our table of antiderivatives or indefinite integrals. What is the antiderivative of 1 over x squared plus 1? Tan inverse. Good. So the antiderivative of 3 over x squared plus 1 would be just 3 tan inverse of x. Okay? Those, like I've said before, those are going to be the tough ones to memorize, I think. The inverse functions, their antiderivatives. All right, and so we're going to evaluate this from 0 to 2. So if you remember from Tuesday, if you were here, which there's a few of you, basically we plug in 2 for x, and we plug in 0 for x, and we take the difference of the 2. And that's how we get the definite integral. So we're going to simplify this a little bit. Each of these pieces over here, that's 0, and tan inverse of 0 is 0. So that second part is just 0. So what we end up with is negative 4 plus 3 tan inverse of 2, just simplifying the right-hand side, or the left-hand side, sorry. And if we plug that into our calculator, we get approximately negative 0.67855. Now, it does say to interpret the result in terms of areas. So what does it tell us that the sum there is negative? Remember, this is an integral from 0 to 2. So we're talking about the area under the curve, or the area between the curve and the x-axis. What does it mean that our total is negative? That's right. The majority of the area is below the x-axis. When we're looking at area under the curve, anything below the x-axis is read as negative area. Anything above is read as positive area. So since our total is negative, that means that this portion underneath the x-axis is greater than the portion above the x-axis. Okay, this is our positive area here, and this is our negative area here. And so we see that since we come up with a total of a negative, we must have more below the x-axis than above. Any questions yet? Okay. Let's take a look at example 6 and just apply some strategies for taking the antiderivative here. Now, when you get into Calc 2, you begin to learn some strategies for some real complicated antiderivatives, such as U substitution. What's the other word? I want to say partial fractions. I don't think that's quite the word, but that's what I'm thinking of. All sorts of different methods. So we're not going to get into anything that complicated in Calc 1, where the focus is more just the derivative and then the applications of basic antiderivatives. So if we're seeing something complicated like this, we've got to understand that there's a simpler way to approach it. So what do you think the best method might be for finding the antiderivative of this function here? How could we rewrite it?
Everything on top times 1 over t squared.
There you go. We can take everything on top times 1 over t squared. So when we do that, okay, we don't change the limits of our derivative or anything. We're just changing the shape of what's inside. So we would get 2 plus radical t minus 1 over t squared, or sometimes I find it easier to find the antiderivative when we look at it as t to the negative 2. So this is going to be equal to what we get when we take the antiderivative evaluated from 1 to 9. So what's the antiderivative of 2 with respect to t? Not x. That's why I said with t. Yep. That's why I said with respect to t. That's our independent variable. So that's going to become 2t. Okay. Radical t. That's another one I find easier to take the antiderivative if I rewrite it as an exponent. So we start by adding 1 to the exponent, which brings it up to t to the 3 over 2. What's going to be our coefficient out front here? Two-thirds. Okay, it's just the reciprocal of whatever our new exponent is. Okay, and if you're not sure, go through and take the derivative and make sure it gets you back to where you started. All right, same with t to the negative 2. We've got to bump that exponent up 1, bringing it to t to the negative 1. Okay, remember, the only time that becomes a natural log is if the denominator is just t, as if it's t to the negative 1. So we bump that negative 2 up to negative 1, and we've got to change the sign out front because we're multiplying by the reciprocal of negative 1. which is just -1. So again, if you're having a hard time, if you're not sure if this is the correct antiderivative, take the derivative. What's the derivative of this piece? What's the derivative of this piece? What's the derivative of this piece? Okay? And it should get you back to where you started. So now to evaluate. To evaluate, we plug in the upper limit for t. And we plug in the lower limit, and we take their difference. That's really all there is to it. The complications are not really in the process here. They're much more in finding the correct antiderivative when your functions get more complicated. But again, that's going to be a Calculus 2 issue. That'll be next semester for you, hopefully. That's when things start to really take off, and we see the applications not just of the integral, but of what we get when we take these figures and we rotate them around an axis, and now we're in a third dimension. We're throwing some volume into it. That gets into some really cool stuff. So the last step is really just to simplify here. 9 to the 3/2, that's the square root of 9 cubed, so that gives us 27, times 2/3 gives us 18. We got 2 and 2/3 and 1. So just a matter of putting these all together. We have 36 and 1/9 minus 3 and 2/3 or 4/9 gives us 32 and 4/9. Any questions there? Okay. So the last thing we're going to look at in this section is the net change theorem, how the integral applies to the rate of change. The integral of a rate of change is the net change. So we have to understand what that means. Net meaning total. What's the total change? So if we're talking about displacement, okay, when we're talking about rate of change being speed or velocity, then it's, the net change talks about total displacement. Not how far you've traveled, but how far you are from where you began. And so you'd have a positive displacement when you're moving away from your starting point. You'd have a negative displacement when you're moving back towards your starting point. So it's possible that you end up back at your starting point. It's possible you end up further away. It's possible that you come back so far that you end up on the other side of your starting point. Because you can be traveling in any direction, really. So there's lots of applications of the integral in this case. For instance, if V of t is the volume of water in a reservoir at time t, then its derivative is the rate at which the water flows into the reservoir. So the integral then would be the total change in volume, okay? How much either came in or came out. Okay? We can apply it to chemical reactions. We can apply it to mass and decay. We can apply it to cost of production of items. We can apply it to current, electrical current. We can apply it in all sorts of different areas. Let's look at the displacement problem first. A particle moves along a line so that its velocity at time t is v of t equals t squared minus t minus 6, measured in meters per second. And we want to find the displacement of the particle during the time period from 1 to 4. So A, believe it or not, A is the easy part. B is a little bit more fidgety, if you will. So when we're looking for displacement, we're looking for a net change. Okay? Where did you end up? So that means we're taking the integral of the velocity function with respect to time. The integral over the interval 1 to 4. So we're going to use the antiderivative of t squared minus t minus 6. All right, so I want you to take a minute or so and come up with the antiderivative of that function. Okay, so what do we have for the antiderivative?
1/3 t cubed minus 1/2 t squared minus 6t.
Good. So now we've got to evaluate over the interval from 1 to 4. Very simple. We plug in 4. And we plug in 1, and we subtract the two quantities. Now, I'm not going to go through all the little bits of calculation in there. I'm going to trust that that's something you know how to do by now. We get exactly 61.6, or approximately 10 and 1/6, or 10.17. And since our velocity was given to us in meters per second, our integral, taken with respect to time, gives us our displacement in just meters. So our net displacement is 10.17 meters. And so what this would tell us, since it's positive, is that in the end, we're 10.17 meters in the positive direction from our starting point, whatever that positive direction may be determined to be. Okay? So since this particle is moving along the line, we'd expect that it's to the right. But it really depends on how the person setting this up defines it. Okay? When we're looking at a real-life application, that positive direction could be north, could be up, could be west, however you want to set it up. All we know is that we end up, in the end, 10.17 meters to the right of where we began. Sorry, in the positive direction of where we began. So the question becomes then, as we look at B, is this total displacement, this net displacement, equal to the total distance traveled?
No.
No, it's not. It's not at all. So, I'm sorry, I've calculated this wrong. I looked at the wrong number. I didn't actually calculate. I stole the numbers from the book. So if you calculated it, you probably came up with the right number. Did anybody come up with the right number? So it's negative 9 over 2 if you plug in the numbers properly. I was looking ahead to the answer at B. That's what happens when you steal your answers from the book. So that tells us, since it's negative, we should be ending up to the left of where we began. So this, as Garrett just said, is not the same as the amount of distance we traveled. This is just where we end up. Negative 4.5 meters, or 4.5 meters in the negative direction of where we started. The problem is is that since we have this particle moving, that particle could have turned around at some point. It could have changed its direction. And when we look at our velocity, that kind of bears out. So consider this. The velocity being t squared minus t minus 6 factors into t minus 3, t plus 2. So it changes direction at a couple of points. The velocity is negative for, is negative for t values less than or equal to 3. Actually we'd put this between -2 and 3. But the key is that up until 3 we have negative values. Now so if we look at the graph of that function, of the velocity function, this is what we see. Now, we are only interested in this interval for when t equals 1 to 4. And the key is this change right here. For the interval from 1 to 3, v of t is negative. So we're heading in the negative direction, which means if we want to get the distance that we traveled, we've got to cancel that negative out, essentially. And then for the interval from 3 to 4, the velocity is positive. So what we're going to do is we're going to split our integral into 2 pieces. And we're going to use the opposite of the definite integral from 1 to 3 so that becomes positive, so that our total displacement becomes a total distance traveled. So we're going to change this just a little bit, and we're going to take the opposite of the integral of t squared minus t minus 6 from 1 to 3. Okay, you can put that negative inside the integral if you want. And then we're going to add in the region from 3 to 4. So this does make the calculations a little more involved, but most of the work we've already done, because we know that the antiderivative of t squared minus t minus 6 is 1/3 t cubed minus 1/2 t squared minus 6t. That we've already calculated. And so we're going to take that integral from 1 to 3 and take its opposite value. Now we're going to take the integral from 3 to 4. So it does become, like I said, more involved, but not necessarily more complicated. Same steps, we got to plug in 3, and then we've got to subtract what we get when we plug in 1. And then we've got to plug in 4 and 3, and I'm already running out of room. So again, this turns the negative area into a positive area, and so that we get a total distance rather than a total displacement. And so this one, sorry, comes out to 61 over 6. Or approximately 10.17. So that's the total distance that the particle moved in that amount of time. Even though it only ended up, as we should have seen in the last one, even though it only ended up negative 4.5 meters from where it started, so 4.5 meters to the left, it traveled a total distance of 10.17 meters. So big difference between displacement and distance. When would the distance and displacement be the same? When would they be equal? The only way they could be equal is if the particle doesn't change direction. That way it ends up exactly as far as it's traveled. So, in other words, if it traveled 4.5 meters to the right, okay, total, the only way that its displacement or its distance could be 4.5 meters is if it never turned around and came back. As soon as it turns around and comes back, we've got a negative distance that we're factoring in there, which changes our displacement. So in order for them to be the same, it can't change direction. Any questions on example 7? All right. So that right there covers evaluating definite integrals. We've got a little bit of time. I want to start to look at some practice problems in this, and we'll start wrong section. I'm looking at the wrong heading. The fundamental theorem of calculus tomorrow. Again, you're going to have an exam next Wednesday, so we're going to be preparing for that. But let me give you some examples that we could work through to get this kind of nailed down a bit. Let's try. I want to mix up some of our integrals a little bit, some of our antiderivatives. So let's start with something pretty basic, I think. So I want you to evaluate this integral, and I want you to remember when you do that radical 3 over z is equal to radical 3 over radical z. That should be a good first step. Let's take a couple minutes and see if we can at least come up with the antiderivative of that, and then we'll work on the evaluation together. All right, let's take a look at this. So the first step is finding the antiderivative. Did anybody come up with that? Okay, Antonio says 2 times the square root of 3 times z. That's one way to look at it. And it's right. I'm just going to approach it a little bit differently to see how he got there. So, ignoring the constant for a second, and just looking at 1 over radical z. This is the same as z to the negative 1/2. So we start by adding 1 to the exponent, bringing it up to 1/2. Then we have to multiply by the reciprocal of the new exponent, which is 2. And so we get 2 times z to the 1/2, or 2 radical z. And we've got to throw that radical 3 back in there. Okay? Bless you. So if we throw that radical 3 and the radical z together in one radical, we get 2 radical 3z. So either format would have been fine. You could have left it like this, or you could put it like this. So then evaluation comes from just plugging in 18 and subtracting what we get when we plug in 1. Okay. Now you can come out with an exact answer. You can leave it like that. The square root of 3 times 18 is going to simplify to 3 radical 6. So you'd have 6 radical 6 minus 2 radical 3 if you wanted to leave it exact. Of course, a decimal answer, if they don't specify, would be fine too. Any questions on that problem? All right, let's look at one just a little more conceptual. This one won't take any work, just some thought. If w prime of t represents the rate of growth of a child in pounds per year, then what does the integral from 5 to 10 of that w prime of t dt represent? Okay, so this is, do we understand what this integral is doing? Now, I'm going to take you back to our notes real quick. This point right here. The integral of a rate of change is the net change. The integral of a rate of change is the net change. So we have a rate of change. The integral has got to be the net change. So let's interpret that in the context of this situation. If w prime of t is the rate of growth of a child in pounds per year, what does that integral represent? What?
You're gaining weight from 5 to 10 years.
Exactly, okay? Although you want to be real careful with using the word gain, a better word would be change, because they could lose, okay? Not likely going from age 5 to 10, but it's possible that they would have less weight. So we would talk about total change.
Hey, we have a fire drill.
That's fine. So we're looking at total change in weight, and as Garrett pointed out, that right there gives us our time frame. From age 5 to age 10. Okay? So this kind of goes back to some of the elementary stuff. Not necessarily elementary, but some of the early algebra stuff we did, where we plotted regression functions, and we said, okay, if we follow this pattern, what function does that fit? And now it's saying we're going to take that function and we're going to reinterpret it as a total change. Okay, so we're taking maybe data that's been plotted, coming up with a function to represent it, and then we're taking its integral to come up with a total or a net change. All right. I think we got time for a couple more. Let's see. Let's go back to one that's a little more concrete. Oh, that's a good one. Let's give this one a try. So your tactic here is going to be to first see what you can cancel out, and then identify maybe what inverse trig function you have. So take a couple minutes and give that a stab. I don't know if I can say stab, public school and all that. But. Can we see what this function would reduce to? One over t squared plus 1. So where we get into trouble with these is we factor the top as well, or we start there. What you want to see is that on the bottom, t to the fourth minus 1 is also a difference of squares. It's the square of t squared and, of course, the square of 1. So that factors into t squared minus 1 and t squared plus 1. So how did I know to look for that? Well, I know that when I have 1 over x squared plus 1, that I have a nice antiderivative in tan inverse. So what I was looking for is a way to get that variable squared plus 1 in the denominator. So of course I've got to cancel out the t squared minus 1. That's what told me to look for that format. So those cancel out. We have 1 over t squared plus 1. And as I already mentioned, that antiderivative is tan inverse of x, or of t in this case, sorry. And we're going to evaluate from 0 to 1 over radical 3. So we're taking tan inverse of 1 over radical 3 and subtracting tan inverse of 0. So we could use our calculator, or you can remember from pre-calculus that tan inverse of 1 over radical 3 is pi over 6, 30 degrees. And tan inverse of 0 is just 0. Any questions on that one? Okay. I'm going to walk you through this next one. At least get you a couple steps into it. Now, the only place that we've used absolute values so far in derivatives and antiderivatives is in when we have the antiderivative of 1 over x and we get the natural log of the absolute value of x. That's not really going to help us here because that's not what's going on. So I think what's helpful, bless you, is to split this into two separate functions. Okay? Because what we have is we have a piecewise function. And if we look at where it splits from positive to negative, and it changes from positive to negative at x equals 1/2, then we have the opposite of 2x minus 1 when x is below 1/2, and we have 2x minus 1 when x is above 1/2. So what we want to do is we want to split this integral into two separate functions. And we're going to say I'm going to take the integral from 0 up to 1/2 of negative 2x plus 1. Okay, that's this right here. And then I'm going to add in the interval from 1/2 to 2 of 2x plus 1. Okay, so we have to remember that a lot of these functions, especially the absolute value functions, are piecewise functions. And if we see where they split, we can split our integral into two separate pieces. Okay? The other option, of course, is even simpler. The other thing you might do is to take a look at the graph. Remember that the integral is the area under the curve. So if we were to graph this, y equals the absolute value of 2x minus 1. I got to think about this and make sure I get it just right. Let's look at it this way. I'm gonna make a table just for the sake of time. I'm gonna just think it through. I got this upside down, don't I? Yeah, I do. Yep. Okay. Perfect. Looks like this. Now what I could do is I could look at this and determine what the area is here and what the area is here and put them together. So I could approach it with a graph geometrically as well to save me a little bit of work. Now that works really well on a basic absolute value function. It wouldn't work really well on a more complicated one like x minus 2 absolute value of x. That would be a completely different story. So think about how you would split that up. All right, so don't forget, exam next Wednesday. You got homework up, and I'll have the videos up later today. Other than that, you guys have a great day.